This is video 14 in our series on tensor calculus. Today we're going to discuss the dot product. The dot product is a very important vector operation that is a prerequisite for understanding many of the future topics of tensor calculus. If you have any experience with the dot product, you probably recognize this expression as the definition for the dot product as given in linear algebra. Unfortunately, this expression is only valid in the Cartesian coordinate system and is therefore completely unacceptable for what we're trying to do in tensor calculus. Now, in most literature, you'll see this expression as an alternate definition for the dot product. In linear algebra, it is derived from the above definition, but in some science literature, this is taken as the actual definition. Purists would argue that it's not a good definition because it assumes that we know what an angle is. They prefer to define it with the previous definition and derive this expression to give a means of calculating a generalized angle within a space. In tensor calculus, we're going to solve both problems by defining the dot product a totally different way. Here's the definition in tensor calculus, and it's something you probably haven't seen before. In this video, we're going to start with this definition and show that we can derive all the necessary properties of the dot product from it, including the two expressions you see at the top of the page. We'll start with two vectors, A and B, that are joined at an angle theta. We'll assume that we know what an angle is, at least for 2 or 3 dimensions. Now, from the definition we just stated, let's see where this leads us. First of all, let's add another vector like this. This vector represents a minus b, and we know that's true because if we add vector b to this new vector a minus b, we'll simply get vector a. Now I'm going to use the law of cosines to find the magnitude of our new vector a minus b. So a minus b, and I'll represent the magnitude with these vertical bars. Really should use double bars, but I'll be a little lazy. So that value squared will be equal to the square of the magnitudes of the two adjacent sides. And again, I'll be lazy and just represent the magnitude with the letter without the vector symbol. I should put these in double bars as well. But I'm going to be lazy here. So now we need to subtract twice the product of the adjacent sides times the cosine of the angle theta. And that's the law of cosines that tells us the magnitude of a minus b. Let me take that off. And now I will extend vector a up here. I'll transport it to a new location. And since vector a is parallel to itself, then the angle that this transported vector makes with b is equal to pi minus theta, because the supplementary angles here are equal to pi. I'll clean this up a little bit, and now we can construct this vector, which is the sum of a and b, and we'll use the law of cosines again to find the magnitude of this vector. So here we have the magnitude squared is equal to the sum of the squares of the adjacent sides minus twice their product and the cosine of the angle between them. But we recognize that the cosine of pi minus theta is the same as the negative cosine of theta. So I can simply replace this term if I will change the sign right over here. So that's what I'll do. Next, we're going to subtract the first equation from the second. So we start with the magnitude of a plus b squared we're going to subtract this term, so it's minus a minus b magnitude squared. And on the right side, you can surely see that these will cancel out when we subtract. And because this is negative, when we subtract, we're going to get 4 of these guys. 4ab cosine theta. Now, what we can do is to divide both sides of this by 4 over here, and that would get rid of this factor of 4. And surely you recognize the left side of the equation to be our definition for the dot product. So we're now down to the fact that the dot product is simply dot product of A dotted into B, according to our definition up top, is equal to this thing, which is simply A, B, cosine theta. And so we have derived the alternate definition for the dot product from our tensor calculus definition. So to keep track of the things that we discover about the dot product, I've started this little fact sheet. So we start with the definition, and now we can add the alternate definition that we just derived. Alright, there are a number of things about the dot product that we can glean just by inspection. First of all, it should be obvious that the dot product with this definition produces a scalar value. A dotted into B, well, the magnitude of A plus B squared minus, the two magnitudes, the difference of them is a scalar divided by 4 is a scalar value. And this expression shows us it's a scalar as well. Well, there's a special case here. Let's ask the question, what happens when we take the dot product of a vector into itself? That's really pretty simple. This expression becomes 2a, and this expression just becomes 0. Well, when I square this, I get 4 magnitude of vector A divided by 4. It should be evident that this is just A squared, or this. And what that tells us is we have a way to define the length of a vector simply by taking the dot product of the vector with itself. The next thing we could do is, using this expression and the alternate definition, we can come up with a generalized formula for an angle in any dimension. Looks like this. We've simply taken this equation and inverted it so that the angle theta is equal to the arc cosine of this expression, and here I've replaced the magnitudes of A and B with the definition of the distance of a vector. So what we have is the definition of an angle in general terms using nothing but the dot product itself. Alright, the next thing that is immediately obvious is that the dot product is commutative. We express that this way, and that's easy to see. It's a trivial exercise to note that this expression up here, A times B is equal to B times A, so this can go in any order, and that in turn would equal times the cosine is B dot A. So the order of the operation does not matter. It is commutative. The other thing that also is immediately obvious is that we can scale the dot product, and that looks like this. If I have a vector CA like this, and I put it into this formula, then the scalar factors of C and D show up in this magnitude formula right here, and of course, being simple scalars, they can come out in this form. So we can always remove the scalar factors as we need to. All right, the next property is a little more difficult, so we're going to have to go back to the chalkboard to look at this one. You'll recognize this as an expression we derived a few minutes ago using vectors a and b. But since we now know that this expression by itself is equal to the dot product, we can modify the expression to look like this. Now, using this as a model, we want to explore what it might look like if we had three vectors. Now, this time, we're going to associate vectors b and c together to represent a single vector. So we've got two vectors added together, and we've got the magnitude squared, so it follows this model. And if we use that model, we can expand it out like this. We're taking the first magnitude of the first vector here. This is the magnitude of the second vector, like this. And then we're adding twice the product of the two vectors. And that's this term here. So that's how we come up with this expression. Okay, but now we have this, which also follows the model. And I can expand it out accordingly. And we'll do that. You can see here that this is the expansion of this term according to the model. So now we've got a full expansion of what it means to take a plus b plus c, magnitude squared. It's equal to all of this expression over on this side. Okay, now having done this, we'll make note of the fact that this was done for an arbitrary set of vectors, a, b, and c. So it's a relationship that's true for any three vectors. So I could simply swap the values of a and c to come up with an expression that gives this to us. And when we do that, I could go through all that algebra again, but I don't need to because I've already got the relationship as it relates to any three vectors. So here I'm simply going to replace a with c and c with a all across the board. And you can see as I replace one with the other, then the expression in purple mirrors the expression in yellow. It's just done for vectors in this order instead of the vectors in the prior order. Okay, what I'm going to do now is I'm going to subtract this expression from this one. So when I subtract them, obviously these two will drop out. A cancels a squared here. These terms will all drop out when I do the subtraction, and I'm going to get negative values for all of these and positive values for all of those. And the expression looks exactly like this. Now we'll do a little cleanup step. We'll divide everything by 2 and move this to the other side of the equation. So now we have this expression. And again, I will emphasize the fact that we're working with arbitrary vectors, so this is a relationship that is true for any three vectors, a, b, c, x, y, z, anything. So if I want to, I can replace all of these vectors with some other vectors or any one of them by a different vector and still maintain the relationship. So what I'm going to do, I'm going to replace vector c with vector negative c. And when I do, watch what happens. Here, the negative c changes this sign, the negative c changes this sign, negative c changes this sign. Now I'm going to add the two equations together. When I do, these two will drop out, these two terms will cancel out, and I'm going to get this guy plus this guy and two of these. So it's going to look like this. Okay, once again, we have an expression that is true for any three vectors. A, B, and C could be anything else. I'm free to swap them around any way I want to and come up with a new expression. This time I'm going to swap the values of B and C. I'm going to trade B for C, C for B throughout the whole equation. And if it's true for this guy, it's going to be true for this. Now I'm going to add these two equations together and watch what happens. First of all, note that this term right here is the negative of this term. If I change this sign to a negative, then I would have to change this and that, and so these two are going to drop out when I do the addition. Also notice that this expression and this one are the same because I can, the order of addition doesn't matter. So when I add these together, I get this. I get two of these guys, and I get each of these terms on the right. And now, in one final step, I'll simply divide everything by 2, and we've arrived at the point we've been trying to get to. This is the distributive property of the dot product. It shows us that A dotted into the sum of B plus C equals A dot B plus A dot C. We say that the operation of the dot product is distributive over vector addition. Now, although this relationship may feel right, and perhaps it's something you already knew, the fact is it's very difficult to prove graphically. What we've done here is to prove it simply by using algebra. And because of that, we can say it's true for any coordinate system. We can also say that it's true regardless of the number of dimensions we're working with. So we can now add the distributive property to our fact sheet. The next thing we want to do is to derive the form that the dot product takes in the Cartesian coordinate system. And for that, we'll go back to the board. Here the proof is almost trivial. I've taken two vectors A and B and expressed them in Cartesian coordinates. Each is represented as a linear combination using the unit vectors, the basis vectors in Cartesian coordinates. Well, now that we know that the distributive property exists, we can distribute each of the terms in the first vector to the second like this, and we can employ the distributive property again to distribute this term into each of the second. We wind up with 9 different terms here. Now, all we have to do is recognize that any of these basis vectors that are perpendicular to each other will result in a dot product of 0, which means that all of these will result in they'll evaluate to 0. So all of those terms drop out. Each of these cases where the unit basis vectors are dotted with themselves will give us just the length. They're unit vectors, so each of these expressions evaluate to 1. Therefore, the only terms that survive are these 3. And that gives us this expression for the dot product in Cartesian coordinates. So we can add that to our fact sheet as well. The last thing we want to do is to determine what it means to take the derivative of the dot product. So we'll go back to the board one more time and see if we can work through that. Here we have vectors A and B, both of which are functions of t. Now as t increases, both of these vectors may change both in direction and in magnitude. So after a small change of t, which we'll refer to as delta t, the vectors might move to a new position that looks something like this. And we'll represent the change of each of these vectors with new vectors we call delta A and delta B. Now to take the derivative of the dot product of A and B, we'll employ our customary definition of the derivative. Looks like this. When the argument is equal to t plus delta t, then the dot product will look like this. We're talking about the dot product between this vector and this one. And the dot product of a and b when the argument is equal to t is this. That's the dot product of this guy and this one. Okay, we now express it this way. Instead of using this vector, we're going to express that term as the sum of these two vectors, which is of course the same thing. We do similar thing up here. Instead of b, we're going to add this vector and this one together to get this expression. Now, because we know the distributive property is true, we can distribute these vectors and expand them out. And the result will look like this. Here we have distributed a to b to get this term, a to delta b to get this one, delta a to this one to get this term, delta a to this one to get this term, and of course we have this term left over. Now you'll see immediately, of course, that this term cancels this one out, and we're left with just three expressions, 1, 2, 3 in the numerator. Well, now I'm going to use the delta t in the denominator to create three separate terms that look this way. Now, a little word here. Obviously, I've taken delta t here to form this ratio. Delta t goes here to form this ratio, but I've got three of them over here. What I've done is I've added two factors of delta t. I've really multiplied this last one by 1, delta t over delta t. So think of it this way. This delta t goes with a, then I created a new one to go with delta b, and another one to match the one I created. So the next thing to do, we've got the expression set up, we just need to take the limit of this expression. And we will remind ourselves of the rules of limits. When you take the limit of a sum of terms, it'll be the same as the sum of the limits of each term. So I can take the limit of each term separately and add them together. Same is true for products. To take the limit of a product of terms, I can take the limit of each factor separately, and the limit of the product is the product of the limit. So what do I get when I take the limit of delta b over t? Well, that's nothing but db over dt. The limit of this guy is just dA with respect to dt. And of course I have the same things here, dA, dt, and dB dt. However, what is the limit of this last extra term? Well, that's not a ratio, it's just a factor. So what happens to delta t as delta t goes to 0? Its limit is 0. Therefore, the 0 factor is going to cause this last term to drop out completely. So our final result comes down to looking like this, but as I say, this extra factor of 0 causes this entire term to drop out. And the final result is what we've been looking for, a formula for the derivative of the dot product. And of course you'll notice that it looks almost identical to the product rule for ordinary functions. Works exactly the same way. The first vector dotted with the derivative of the second plus the derivative of the first dotted with the second. Works the same way, and the proof of it is almost identical to what you'd use to prove the product rule for ordinary functions. So we're ready now to add that as our final fact to our fact sheet. And with that, we can bring this video to a close. Next time, we'll use the dot product to define what we call the covariant metric tensor.